The producer-consumer problem is like a bakery where bakers, who are producers, bake loaves of bread, and delivery drivers, who are consumers, take the loaves to the shop. The bakery has a limited shelf, which is the buffer that can hold only a certain number of loaves. If the shelf is full, bakers must wait before putting more bread, and if the shelf is empty, drivers must wait for fresh loaves. Video streaming, the decoder produces frames and the display consumes them. Printing systems, print jobs are produced by applications and consumed by a printer. Sensor data pipelines, sensors produce measurements and the analysis code consumes them. A critical section is a part of a program that must be used by only one person or thread at a time, like a single-person checkout line at a store. Mutual exclusion is the rule that says no two people can be in that line together. A race condition happens when two people try to use the same resource at the same time, and the final result depends on who gets there first, like two children trying to take the last cookie from a plate. Who grabs it first decides who gets it, and the other child ends up with nothing. In a computer, if two threads write to the same variable without coordination, the value can become unpredictable. The bounded buffer is a small array that works like a row of mailboxes. It can hold at most n items. Two indexes are kept: in, the position where the next produced item will be placed, and out, the position where the next consumed item will be taken. When a producer puts an item, it writes to buffer of in and then moves in equals in plus 1 modulo n. When a consumer takes an item, it reads from buffer of out and then moves out equals out plus 1 modulo n. The modulo operation makes the indexes wrap around, turning the line of mailboxes into a circle. Semaphores are like colored tokens that tell a thread whether it may proceed. 3 semaphores are used. Empty counts how many empty slots are left, starts at n. Full counts how many filled slots exist, starts at 0. Mutex is a binary semaphore, value 1, that protects the critical section where the buffer is actually updated. The producer does P empty take a token that says there is space. P mutex enter critical section. Buffer at index in equals item put item. In equals in plus 1 modulo ends. V mutex leave critical section. V full announce one more full slot. The consumer does the opposite. P full wait for an item to be present. P mutex item equals buffer at index out take item. Out equals out plus 1 modulo ends. V mutex V empty announce one more empty slot. P, also called wait, decreases the semaphore and may block if the value would become negative. V, also called signal, increases the semaphore and may wake a blocked thread. A monitor groups the buffer and its synchronization tools into one object, much like a librarian who guards the bookshelf. Inside the monitor we have two condition variables, not full and not empty. Procedure produce open parenthesis item close parenthesis open brace. If open parenthesis count equals n close parenthesis wait open parenthesis not full close parenthesis semicolon shelf is full wait buffer open bracket in close bracket equals item semicolon in equals open parenthesis in plus 1 close parenthesis modulo n semicolon count plus semicolon signal open parenthesis not empty close parenthesis semicolon tell a waiting consumer close brace. Procedure consume open parenthesis close parenthesis returns open parenthesis item close parenthesis open brace. If open parenthesis count equals 0 close parenthesis wait open parenthesis not empty close parenthesis semicolon shelf empty wait item equals buffer open bracket out close bracket semicolon out equals open parenthesis out plus 1 close parenthesis modulo n semicolon count minus semicolon signal open parenthesis not full close parenthesis semicolon. Tell a waiting producer return item semicolon close brace. Wait releases the monitor lock and puts the thread to sleep on the chosen condition. Signal wakes one thread that is sleeping on that condition. The monitor guarantees that only one thread executes inside the procedure at a time, so the critical section is automatically protected. To prove the solution works, we define two invariants. Count invariant, 0 less than or equal to count less than or equal to n at every moment. This means the buffer never has negative items and never exceeds its capacity. Index invariant, in and out are always valid indexes, 0 less than or equal to in, out less than n. If a producer executes produce, It can only add an item when count is less than n, checked by weight not full, then it increments count. Therefore, the count invariant stays true. The consumer can only remove when count is greater than 0, then it decrements count. Hence, the invariant never breaks. Deadlock freedom comes from the fact that each weight has a matching signal that eventually runs, because producers and consumers are infinite loops. No circular weight can arise because a thread never holds both not full and not empty simultaneously. It holds the monitor lock, checks a condition, and if it has to wait, it releases the lock, allowing the other side to run and produce the needed signal. Throughput is the number of items processed per unit of time, usually written as T equals items divided by time. Latency is the average time an item spends waiting in the buffer before it is consumed. Buffer utilization is the average number of occupied slots divided by the total size n. If the producer is fast and the consumer is slow, full will often be at its maximum, the buffer utilization will be close to 1, throughput will be limited by the consumer, and latency will grow because items sit in the buffer longer. If the consumer is fast and the producer is slow, empty will be high, utilization will be low, and latency will be small. The optimal point is when producer and consumer rates are balanced, giving high throughput with moderate utilization and low latency. The producer-consumer system can be modeled as an M/M/1/KQ where M equals memoryless Poisson arrival of items at rate lambda. M equals memoryless service time for consumers at rate mu. 1 equals a single server, the single critical section that removes items. K equals the buffer capacity, n including the one item possibly being serviced. The steady-state probability that there are I items in the system is P sub I equals open parenthesis lambda over mu close parenthesis to the power of I divided by I factorial close parenthesis times P sub 0 for I equals 0 to K birth-death process. When lambda not equal to mu, a simpler closed form is rho equals lambda over mu. P sub 0 equals open parenthesis 1 minus rho close parenthesis divided by open parenthesis 1 minus rho to the power of K plus 1 close parenthesis. P sub I equals rho to the power of I times P sub 0. Throughput effective service rate is lambda effective equals lambda times open parenthesis 1 minus P sub K close parenthesis. Because arrivals are blocked when the buffer is full, P sub K is the probability of being in state K. Utilization is U equals the sum from I equals 1 to K of I times P sub I divided by K. For example, with lambda equals 5 items per second, mu equals 6 items per second, and n equals K equals 4, we get rho equals 5 over 6 approximately 0.833 P sub 0 equals open parenthesis 1 minus 0.833 close parenthesis divided by open parenthesis 1 minus 0.833 to the power of 5 close parenthesis approximately 0.167 over open parenthesis 1 minus 0.40. 1 close parenthesis approximately 0.167 over 0.599, approximately 0.279. Then P sub 4 equals rho to the power of 4 times P sub 0, approximately 0.833 to the power of 4 times 0.279, approximately 0.48 times 0.279, approximately 0.134. Thus, the effective arrival rate is lambda effective equals 5 times open parenthesis 1 minus 0.134 close parenthesis, approximately 4.33 items per second. This shows how the finite buffer limits throughput, and how the mathematical model predicts the same behavior described in the earlier sections.